Hey, pre-class announcements. What do we have going on in this class? We have an assignment due on Friday. And you will be getting a new assignment probably about Friday. Today's task is to finish up coding quicksort and to start introducing binary search trees and just trees in general. So starting on Friday, you are likely to be getting a binary search tree assignment. That is the bad news. The good news is it is the last required assignment in the class. So what is coming after that is an optional assignment on graphs. Graphs aren't really supposed to be covered in here, but I like to at least introduce people to them because that can be one of the sticking points moving between data structures and algorithms. So what I will say is you submit that assignment and I will drop your lowest assignment score from the quarter. I'll replace that with the lowest score. If that happens to be the lowest score, then I'll just pretend like you didn't submit it. But you'll still get feedback on it, so it's still valuable. Questions about where we are, what we're doing? Are we ready to dive in? Yeah.
Does that count for the 200 point assignment?
I would, that is a great question. I would replace the percentage of the 200 point assignment. Yeah. I would do that. I like advertising it after the fact, so people have a reason to submit the 200 point assignment. It's kind of important for your learning outcomes, but we'll spread it to the next data structures class they teach, even though it won't be for more than a year. Yeah. If you're still around and doing that, and remember, then we want people to do the work. Anyway, last time we were in the middle of quicksort. Well, we kind of just started quicksort. We had done just this basic quicksort. We made a public-private split between them so that the user just calls the public version, since the user shouldn't need to know anything about the fact that quicksort uses a low index and a high index and what those initial values should be. We can hard code those initial values right here. And that means that it's abstracted from the user, which is very good. Inside of the private method, we just said it's really just 3 steps. We figure out where we're going to partition, and then we recursively call quicksort on the left half and the right half. Of course, figuring out where we're going to partition is almost all of the work. So this is a nice high-level abstraction of quicksort, but in order to actually have this working, we need to make sure that we implement that partition. We figure out where is it that we are partitioning. So let's go ahead and write this. Privacy of partition, should it be public or private, and why? Yes, it really makes sense for it to be private. This isn't something that the user should be thinking about or calling. It's part of this algorithm, but it's not part of what the user should be concerned with. So let's certainly make it private. Like everything else in here, it's going to be static, which means that we're not instantiating quicksorts. When you implement this for your homework, you will be instantiating quicksort objects, so these methods will not be static. Oh yeah, you were gonna remind me about that today. That was not anywhere near vicious enough for my forgetting something. You're too nice. All right, so yeah, big important announcements for the homework. I did not change much of the wording from the last time that I'd given it, even though I've done a bit of restructuring in terms of how this course's assignments are working, since we're trying to implement the strategy pattern in our linked lists and sorts. So rather than just implementing this for a singly linked list and writing it in the singly linked list class, you should be making new classes both for merge sort and quicksort, and those classes would implement your sort interface. That way you don't need to worry about anything related to a singly linked list, since we've already done that abstraction. It will work for all of your lists with no additional work on your end. This is really the payoff for having implemented the strategy pattern earlier in the quarter, is that now we can add new sorting classes without making any changes whatsoever to our list classes or our other sort classes. So we just need to write those new classes. And then since we haven't actually done design patterns for this, you will need to go in your set sort method and allow for the options of setting new merge sort objects or new quick sort objects. So those should be really the only changes. Then for submission, just zip everything up. Zip up everything from the sort interface and sorts to the list interface and lists, and that way we can just run your entire project with our own custom driver.
Can we send an announcement out for those?
Yes, yeah, I will also edit the document. I think that's the easy, I'll post an announcement that I've edited the document with all of that information, but I wanted to make sure that you heard it from me in person first. And not just randomly get an update a couple days before the assignment is due. It's actually going to be easier. This assignment was made easier with the more difficult work that we did earlier in the quarter. And that is the whole purpose of design patterns, is to make that future work. Okay, thank you for the reminder. I do have the memory of a goldfish, even though we talked about it about 3 times yesterday. I'm gonna forget, and then I do. So we're going to be partitioning. We still need these exact 3 same parameters. So that just means we could combine them, but as we know, with writing our methods, it's very nice when we are able to abstract and separate the logic a bit. It makes it a little bit easier. So what did we say in quicksort? Where are we finding the pivot? Where is the pivot located? The example that we gave was at the start. I'm actually going to code the exact opposite so that we kind of see how it works from the low end on the example and the high end and what the differences are. But in reality, it doesn't actually matter as long as you're consistent, unless we believe that there is some kind of underlying structure to this data. If we believe it's likely to be in reverse sorted order, then we don't want to take the first or last element, because then quicksort is going to behave closer to its worst case behavior than its best case or average case behavior. So we're going to set a partition. Partition of the pivot. We'll set the pivot to be the last element in the array. And luckily, we're passing that in as high index, so we can just use that. I'm also going to I'm going to rename low index for the moment, just because we don't want to type it out a bunch of times. And I'm going to make another equal to, since we're setting the pivot to be the high index, this is going to be the pointer that points to where low index is moving. That is I. Then J is going to be where the higher value is, as we're looking for. We want I to be, or I guess R of I, array of I, to be something that is larger than the pivot, and R of J, as I'm about to make, to be something that is less than the pivot, so that we swap them when we get there. So we want to start not at the pivot, but at the pivot -1. Since we know the pivot is the value that is at the array of I index, the first element that could potentially be something that is swapped, since we're not ready to swap the pivot into place yet, would be the element before the pivot. And I'm not using the values here, I'm just using the indices to keep track of that. So that's our prior work going into identifying the pivot. Where should we go from here? What kind of construct should we be producing? Yeah. So we need some kind of loop that's going to point I at something that's larger than the pivot and point J at something that is less than the pivot so that we can swap them. Yeah, so we want some kind of while loop. This is going to be a for. We don't know how many times this is going to run. We have to figure this out as we go. So what are the conditions in this loop? Let's first focus on I and having I go find something larger than the pivot. So what goes in here?
Oh, I was reading. And then you also want J to be less than. The pivot to want that to both be true. So
Yeah. Yeah, your logic is right there. The first thing is that we want to be pointing at the element of the array and not the index. So we're going to check in the array R of I. And then you said greater than, we want to continue as long as it's less than or equal to, because we're looking for something that is greater than. That is a great point, though. It's exactly what we should be thinking about here. So while that array is less than or equal to our pivot, since our pivot's storing the actual value, we're comparing here value to value. We're not using any indices. We can say, well, that is true. There's one other condition that we should be aware of. What is that condition?
all of like. opposites lie.
Yeah, we want to make sure that they haven't crossed over, because as soon as I is greater than J, we know that we finished identifying elements that need to swap. So we're ready to swap the pivot into place. So yes, one more condition here. We want to say that I is less than J. As we do this, the only thing we need to do in this loop is bump up I. Because all we're doing is identifying the position of the first element that is greater than the pivot in this array. That's it. We're going to do exactly the same thing with a second loop, except we're going to be bumping down J. So now we care about the array with respect to position J. That should be now, instead of less than or equal to the pivot, we're going to continue while we're looking at elements that are greater than or equal to the pivot. As soon as this is false, that is the first element that we have found that is less than the pivot. And we still want to continue to do this while I is less than J. We don't want to change that up at all. As we do that, we will just bump down J. As these loops terminate, we have found something to swap. So we're going to do that. We can write our own swap, why not? We're going to be doing this possibly in a couple places, so let's just swap, and we can pass it three things, the array that we're doing, and we want to swap what's at element I with what's at element J. Let's quickly write our swap. Who wants to write the swap for me? We've done this a couple of times, so what procedure do we want to use to swap? Do we want to swap with a temp? Do we want to swap in place without a temporary third variable? What do we want to do?
Use a temp.
Use the temp. That's usually if you need to implement it quickly, don't worry about using an extra variable. We aren't back in the 60s. We're not that constrained on memory. How do we do that? Swapping with a temp.
Oh, you want that temp.
Yep. We know this is an integer array, so we can set temp as an int. In our programs, we've been setting temp as a t because we're generically programming things. In this case, we are not. So temp can be that. Do we want temp to be what's at position I or position J? I. Sure. It doesn't actually matter. Again, as long as you're consistent with this, we'll do that. What's the next line? We want to overwrite that element that we just stored off. Make sure that that goes here. If this was R of J, then you want to overwrite R of J. And then finally, we want to set R of J to be 10. Great. There's our swap.
So we need to return a partition.
Yeah, from this partition, we need to return an int of some kind, but what is swap concerned with? It needs to be static. Of course it does. All right. Questions on anything so far? Yeah,
Oh, why, the second line is supposed to be greater than or equal to what's greater than.
is supposed to be. Yeah, we don't want to continue this while it's equal, do we?
Usually it's less than or equal.
Yeah, and greater than or equal.
Feels wrong.
Yeah, we should only have it for one, because we want to bias it. Well, what's funny is it won't matter, because if it's equal to, then it'll actually be handled here and not here. But I do think this is cleaner. I think you're absolutely right, that it's cleaner to have the greater than here. Good catch. What else aren't we thinking about? So kind of continuing from here, we've done this once. We've identified the first swap. Great. Is it possible there would be more than one swap? So maybe we should surround this entire logic in another loop that continues finding elements, swapping them, finding elements, swapping them, finding elements, swapping them, until what's the termination condition when we are done finding and swapping those elements? Well, not necessarily. Once we're ready to swap the pivot into place. But what has to be true in order for us to, I think you're absolutely right with that. What's true in order to swap the pivot into place?
The low index and the high index are the same.
Yeah, we're gonna actually use I and J for that, but I think you have the exact right idea here, that once I and J do switch to the point where I is greater than J, then we should be done. So we're actually gonna surround this entire logic with while I is less than J. As soon as it becomes equal to J, we know that we have overlapped, and now we're ready to swap the partition into place. So we're going to do that, and format. Yeah, we're definitely not done yet.
Oh,
We are not quite done yet, but we're getting close. So now the question is, are we continuing with this loop or are we done with this loop? Is there anything else that we need to do to prepare to swap the pivot into place? Silence is good here, we're done. So to swap the pivot into place, we need to do something. What does it look like to swap the pivot into place? Luckily, we already wrote a swap. So we can reuse the swap.
asking us what we're returning, or
We need to swap the pivot into place before we're ready to return.
but you know, we already swap or.
We swapped when we found elements as we marched down, up and down the array at the same time. We found elements that were larger than the pivot and smaller than the pivot, and we swapped those. And eventually we converged to a position. Now we need to take the pivot, the last element in the array, and swap that into place. With, now is it gonna be I or J? Take a minute to think about this. I think that's a very important part of this. As we went over the example on the board, we ended up with a left and a right, and we swapped with wherever right was pointing. But now we are looking at the partition being the last element in the array. So what makes sense as the swap here? We certainly want to call swap. We're going to pass it the array. We're going to pass it something, and then we're going to pass it the position of the pivot, which is at high index. So that's going to be our swap call. We just need that middle parameter. Should it be I or should it be J, and why? Yeah,
I feel like it's J, but, I feel like it's J because we already did the outer, like, we already figured out where to swap the variables. You know, like, when we're going through the values.
yeah.
So I
Think about what happens when they cross places. So we know that since the pivot is at the end, we want to swap this with an element that is going to be greater than the pivot. Once I is marching up and J is marching down and they cross, it is I that's going to be pointing to the thing that is greater than the pivot, not J. So we can swap with I, and the element at the end now is still going to be greater than the pivot. So the answer is unfortunately I, but that is why. Once they change positions and I is greater than J, which is the termination condition of this loop. In order for this loop to terminate, I has to be greater than or equal to J. Question?
Why would we need I less than J in the inner while loops if we have an outer while loop there? Is it because there's an instance where you would get it not necessarily C?
Yeah, we want it to swap, we don't want it to keep going
Okay.
at that point. That is a very good question, though. We do need this to make sure that we stop this point if we cross over. All right, so that's our swap. It turns out that this is actually not something we want to do all of the time. What is the instance where this is not what we want to do? Yeah,
If the array is size 2, that's
yeah, kind of either a small value like that, or the fact that the item that we found is not greater than the pivot for some reason. So that is that case of 2, where in that case of 2, we found that we were out of order sometimes. So the way that we're going to handle that special case here is we're just going to surround this swap with an if. And it's basically just going to say, if this value that we found at position I is greater than the pivot, which is what it needs to be in order to want to swap them, then that is exactly what we are going to do. Else, there is one thing to do, and it's just to set I to be the I index. Why do we want to set I to be the high index? What is it that we're returning? Where we are partitioning. So I is the correct location of where we are partitioning, and where we swapped the pivot into place. That is where we want the partition, unless it wasn't in that base case of size 2 where this logic doesn't work. So setting I to high index, that tells us that the partition was at the pivot. So rather than partitioning somewhere near the middle of the array, we actually partitioned at the end of the array where the pivot was, which is the worst case behavior of this algorithm. But again, if it's an occasional thing, then it's not a big deal. It's only if the array is sorted or reverse sorted, and this is consistently going to be the case. So we do this right before we return I as the partition. So that's the entirety of the partition. This is about as long as I want a method to be. In reality, it's already feeling a little bit long, but we did take out swap, which was good. And it turns out that this completes quicksort. It is done. Could write a tester for it real quick, just to make sure that I haven't totally misled you in some capacity. So let's do that. Give me some numbers. Our favorite in-class activity. That 2 people like participating.
7. 524. -23.
29.
One more,
13.
favorite number. Gotta get it in there somewhere. All right, so then we just call quicksort on that. And remember, from the end user's perspective, we're now calling the public version of quicksort, which will call the private version for us. We don't have to worry about what that low index and high index initial values are. Very nice. It's great to be an end user of a product that has been well thought through when it was designed. And then once we are done, we just print out. Let's see, this one, arrays dot toString, doesn't matter which one we call, because we just pass it the name of the array, run it. That didn't work. Didn't work on the negative. Got everything else. I will look into this to not waste your time with it, but there's a small issue. I'll figure it out before I make this code live for you to use for your homework. Questions on this implementation? Does anyone see the bug instantly? I'm wondering if this is because it's an odd length. Let's test this with one more value. Still doesn't work, and it's still perfect aside from the negative number. That is very strange to me. I will have fun in my own office hours.
Is it because it's not, and, I don't know. I suppose it doesn't matter on sign or something.
Not bad. All right, I'm not wasting your time. I'll have a solution for you eventually. All right, last thing we should talk about with regards to quicksort is its complexity. Unlike merge sort, it does have a worst case, and we've been seeing that as we've been looking through this. We have found that if we're not swapping the pivot somewhere in the middle, and we're continuously seeing that the pivot is the first or last element once we are done, then this is a quadratic algorithm. It's no better than bubble sort or insertion sort or selection sort. It's just quadratic. But if you can frequently or always get that pivot somewhere in the middle, then we have another log linear algorithm. So n log n, just like merge sort. And in fact, and I think we already saw this when we drew it out, we saw that the recursive depth is proportional to the log of the size of the array that we're sorting. So everything combined takes n log n time, which is great. This is both an average case and a best case. But the worst case is actually quadratic. Just like merge sort was the default sort in Java, quicksort is the default sort in C++ and other efficiency-oriented languages, which is cool. Although it creates an interesting question to ask about why would something with a worst case quadratic behavior be used in efficiency-oriented languages over something that is a worst case log linear algorithm? And the answer boils down to this ends up being more efficient on the case-by-case basis. So it's a constant time speed up, but it's a speed up that in efficiency-oriented language is an important one to make. Any further questions on either of these sorts? Obviously, it would be ideal if I had actually written this out and run it beforehand. All right, we're going to dive into the next unit. All right, trees are what we're gonna spend quite a bit of a reasonable amount of time on because they are extremely important structures in computer science. So one of the main structures used just about everywhere. So everything we have learned this quarter is probably the most widely used and applicable. Because we have now learned about recursion, recursion is very frequently used in trees because tree substructures are also trees. And that means that you can very efficiently store and search for data using a tree structure, especially if you have some way of intelligently knowing where to search in the tree. We've actually already gone over this example because sometimes I like to use my later examples earlier on in my class, but we've actually already drawn out trees, and let's refresh you on the concept of just guessing a number between 1 and n. So we're playing a game. I say I'm thinking of a number between 1 and some power of 2 minus 1. And then the question I ask you is, if I tell you after every guess, your guess was too high, too low, or spot on, what are the maximum number of guesses that you would need in order to guess that number? So we can draw this out with size 7, that's a power of 2 minus 1, and you get a tree of depth 3. And if we store the numbers as such, these are kind of small circles for everyone to see. We have 1, 2, 3, 4, 5, 6, and 7. Then you can see what your guessing strategy should be. The very first thing you should guess is 4, because that splits the space directly in half. If I say your guess was too high, it's lower than that, then you know you've isolated it to this branch of the tree. If I say your guess was too low, you've isolated it to this branch of the tree. And the size of this is equal to the size of that, so you have maximally gained information from this. In the worst case, you have eliminated half plus 1 of the numbers that it could be. So let's say I say it's too high, it's somewhere in here. The next guess should be 2, because now there's only 1 number. And you can guarantee that within 3 guesses of the depth of this tree, that you will have guessed the number. What's amazing and beautiful is that this is just the left half of the tree of doubling the number of numbers. So if I said I'm thinking of a number between 1 and 15, the next power of 2 minus 1, this is just the left subtree of what would be, you'd have something down here that's an exact copy of this triangle. So you can double the size of the numbers that you're guessing with just 1 extra guess. So that's kind of our motivation of starting to think about tree-like structures, is they can answer quite a few interesting queries about sorted data or data that you know has some kind of sorted feature to it. And it doesn't have to be numbers. We can sort strings, we can sort custom-made objects. If we have people objects, we can decide that people objects are sorted by age. They're sorted by anything else we care about. Height, salary, whatever we store in a person object, we can make a comparator and compare to that allow us to sort that object in that way, meaning we could then store those objects in a tree sorted in that order, and we could identify our target search. If we're trying to find a person, we could find that person in logarithmic time, as long as that tree is what we call balanced. And we'll get into that in a bit. So moving past linear structures, finally, it's only taken us weeks and weeks and weeks, but every structure we've looked at so far has kind of a beginning and an end. Any kind of list that we talked about, a hash table, all of those utilize linear structures. But a tree is not a linear structure. A tree is kind of a 2-dimensional structure. So linear structures have a concept of before and after. You know, what is it, this index minus 1? What is it, this index plus 1? But trees have a hierarchical structure, meaning they have parents and children. You start to think of it like some kind of family tree. So let's go over all of the important tree terms that I'm going to use. I've already used a few of them. The root is the base of the tree. So in the tree structure that I just drew, the node that had value 4 was the root of the tree. When you start a query, that is where you begin. I'm thinking of a number between 1 and 7. What is your first guess? The first guess would be at the root of the tree. Given that you have a node, the parent of that node is 1 level closer to the root. So we saw that, for instance, the node 2 had a parent that was the root 4. Parents can have any number of children. So a connected node, meaning that there's an edge between this node and another node, and that other node is a 1 depth further from the root. So a node can have an arbitrary number of children. A binary tree will only have 2 children. But in general, there's nothing that says that a tree only needs 2 children. We will distinguish between trees and binary trees in a bit. Siblings are 2 nodes that share a parent. So because of this, they must be at the same depth in order to do that. A key is what we're going to call the data that we store in a node. So the actual number that was in there, you can call that the value, or it's especially relevant to call it the key, because we were going to use trees when we start talking about maps. An internal node is any node that is not the root. Subtree is a recursive definition of a tree. So we can see that if we take a tree and we say, all right, for the root, everything that is descended from the root's left child, that is also a tree with its own root, the left child of a parent. Leaf node is a node that has no children. It means it's as deep into the tree as we can get. There are no further children. So, bunch of terms. Any questions on any of these terms? All right, some more of them. An edge is just what we're going to call the connection between 2 nodes. If we want to define the height of the tree, a tree starts, or I guess I want to pair height and depth because these are frequently confused. So the height of the tree, a tree starts at, the root is at depth 0. It's not at depth 1. So because of this, the height in terms of that is the number of edges that connect the root to the deepest leaf node. So what is the longest traversal path down this tree in terms of the number of transitions that we would need to make? It's the number of nodes in that -1, since the root is at depth 0, the height 0, depth 0. So that's the height. The depth can be queried for any node in the tree, and that's just now the number of traversals that we need to get to that node. So let's again just draw out the same tree that we had before, just so we can get a sense of a few of these terms. Shouldn't have erased it in the first place. All right, so 3 is a leaf. 3 has a parent that is 2. 2 has children, 1 and 3. 5 and 7 are siblings because they share a parent. The height of this tree is 2. We have depth 0, 1, and 2, and the maximum depth of this tree is 2. So the height of this tree is 2. The depth of 6 is 1. The depth of 5 is 2. The depth of 4 is 0. And each of these are keys within their associated nodes. We have nodes, and then these lines are our edges. we can call a set of nodes that share a depth, a level. So this is the tree at level 1. This is the tree at level 2. And you can see that this becomes a set. We could define any of these as the set 1, 3, 5, and 7. Question?
I guess what if this is a tree, would this ever be a tree where you have the same value in multiple nodes?
Yes, and then defining that as a set could be a bit tricky. Yeah, maybe you want this to be a list if duplicates are allowed. In something like a binary search tree, it becomes a little bit difficult. You have to store duplicates, we have to do a little bit of extra logic. But yeah, if duplicates are allowed, then it should be a list and not a set. An ancestor just says if we can query parent, we eventually get there. So 4 is an ancestor of 5 because we query 5's parent is 6, 6's parent is 4, and we got there. So thinking about it like a family tree will help a lot in terms of some of these terms are based on that concept. And a descendant is exactly the same but in reverse. A descendant of 4 is somewhere where we can query some child, and eventually get there. So 5 is a descendant of 4 because 6 is a child of 4 and 5 is a child of 6. Note that if we're querying an ancestor, each node only ever has one parent. So there's no searching to be done. But if we're trying to figure out if a particular node is a descendant of another, now we actually have to search for it. So we need some kind of either intelligent layout that says if it's in the tree, it's going to be down this particular branch. Or we need some intelligent searching mechanism to be able to say, we need to exhaustively search all possible children and children of children and children of children of children until we reveal it. Which is why it's very important that these trees have some kind of order to make that search much more efficient. And one final point to note is we cannot have a cycle in a tree. We can't go from a node to itself. One's child cannot be 4. We can't query descendant, and end up with yourself. Or ancestor, and end up with yourself. No time travel is allowed in trees. It would blow your mind to learn that you are your own great-grandparent, your own great-great-grandparent. There are songs, there are movies, there are all sorts. We don't allow that. That breaks reality. Fun in movies, not fun in computer science. All right, any questions about any of these terms? Actually, let's ask that question while showing this. So here are all of the terms that we just went over embedded in one structure. So take a look at this for a little bit. Anything not make sense? Anything ambiguous? Everything here makes sense? What can I explain in more detail?
Will a tree always be organized top down, left, right?
So yeah, not necessarily, but it will be if you in particular orderings. We'll actually talk about the different ways to traverse a tree. So if you start at the root and then you were to say, let's go from left child to right child and insert all of these into a queue, then the order in which we visited those nodes would be these letters. From A, we would add B and C into a queue. Since it's in a queue, the first thing we would look at is B. Then we would add into that queue D and E. What's the first element in the queue? C. We would add G and F into the queue. What's the first element in the queue? It's now D. So you see that we'd be doing a level order traversal if we did that. But there are plenty of other ways. If we saw in the guessing game, the first element lexicographically was this very bottom left element down here. So it depends on how you traverse the tree. Great question. Let's take a look at now, if we're gonna convert this idea into code, how would we start to do this? So what should a node store? Thinking about a node object. What data do we need in this node? What fields would we put in?
The parent child.
Yeah, some kind of key or data. And we would need some kind of array of children. And an optional parent. Depending on the use of this tree, if it's worth querying parent, sometimes it is not worth querying parent. Sometimes you can also get to that question, kind of like with a singly linked list with a find node before. You could have some kind of find parent of a particular node if you needed to. But if you were going to query that frequently, then maybe it's worth the memory cost of making each one of these objects store a parent node. Again, we frequently see this in data structures, there's that time-space trade-off. If we store the parent, we don't have to search for it. If we don't store the parent, we have to search for it when we need it. What methods should we have inside of the node class? This is not the tree class, this is not anything larger than just the individual circle in a tree that stores something and its associated connections. Be able to at least get the data. If we're storing all of these private, as we should be, we should at least write some getters for all of the fields and possibly some setters depending on the implementation and whether we want full read-write access to this. Of course, we can make it protected and throw everything in a package that we needed to be able to set this, and then the end user wouldn't be able to modify the tree, but our own other classes that are related to this could modify the tree. How about the tree object itself? The tree is going to be made up of these tree node objects. Makes sense? A tree is really just a bunch of nodes and their associated connections. So what fields do we want in the tree object? What do we need to define a particular tree?
That node as well as like the size of the tree.
Yeah, we need a single node. We don't need to store all of the nodes. We just need to store the root. Because if we query and get the root node, we can see the root's children from the fact that each node stores its children. So we don't need anything from that in the tree object itself. The tree object is, we just need to know, where do we start? What is the initial node that we should be looking at when we begin some kind of query about this tree? And that's it, really. For some applications of a tree, you will want to store more than this. If we're trying to make sure that our tree stays balanced, then we would need to store some more. Question?
Yeah, would we not need to use the key as one of our fields?
A key would be for a particular node. So like what's if we wanted to know the root's value, then we would get the root node and then query its key. If we wanted to get the root's child, right's child's, left's child's key, then we would use that root node to. Since that stores an array of children, you would look at that index 1, that would get you the right child, that index 0 will get you the left child, then you would query that node's data to get access to that part of the tree. So it's actually really difficult to visualize the entire tree just from this structure. That's going to be some functionality that we want to add to our tree to be able to say, given that we have a tree, it would be useful for me, the human, to be able to see what is in this tree. That said, even that's kind of a challenge because how do you print out a tree? We'll get into that. That's kind of a fun problem. How do you visualize and write a visualizer for a tree? So methods, we want something like element. This would just return the data of some node V. And now we would write that says, all right, now we need to search for it. Once we find it, we return that data. So if we have access to a node object, then grab its data. Get root returns the root node of the tree. Parent allows us to return the parent, not the print, of a node. And then children gives us some kind of container that we want to be able to iterate over holding the children. We can write is internal. to determine whether a node is basically not the root. If it exists in the tree structure and is not the root. Is external. Returns whether it is the root. Is root. Size is empty, tells us whether there's nothing in the tree. Is the root null? And positions and elements return both iterable lists of either all nodes in the tree or all data in all nodes in the tree. Finally, we can write a replace the contents of node V with some element E. Replace also returns that old value in case the user needs to use it for some reason. There are actually a few more of them. Now, I'm going to leave it at this for the day since we are technically out of time. We will come back to this tomorrow and look at this in more detail and start asking questions about implementing trees. Because this is certainly a more challenging structure than anything we have seen so far. But yeah, that's where we are. Let me know if you have questions. I have office hours starting right now. Anyone who would like assistance on the current assignment or any clarifications.
Your initial public call.